In this chapter, we're going to continue talking about energy. Only now we're going to discuss energy in terms of electromagnetic radiation. In other words, light. We're going to learn about how light can interact with different atoms and molecules, and how that interaction led to the discovery of the electronic structure. Energy can be transferred as light. Invisible light is just one region of the full electromagnetic spectrum. Electromagnetic radiation can be used to determine the energies of electrons within various atoms and molecules. It also allows us to study the structure of atoms and molecules. Spectroscopy is a whole branch of chemistry that deals with the sample of matter being interacted with different forms of electromagnetic radiation, and it allows us to determine different properties of our compounds. The electromagnetic spectrum shows us all the types of electromagnetic radiation. Each type has a range of specific frequencies and wavelengths that's associated with it. On the far right side, we have low energy radiation. These are going to have long wavelengths and short frequencies. On the left-hand side, we have high energy radiation. This electromagnetic radiation will have high frequencies and low wavelengths. We can see that there's an inverse relationship between frequency and wavelength. Low energy radiation includes radio waves and television waves, microwaves, and infrared radiation. Visible light is just the small portion of the electromagnetic spectrum that we can actually see. If visible light is used as kind of a middle ground, the radiation to the right of visible light would be considered low energy, and the radiation to the left of visible light will be considered high energy. Visible light can be seen from 400 nanometers up to 700 nanometers, with 400 being in the violet region and 700 being in the red region. Roy G. Biv tells us all the colors that we can see in the visible portion of the electromagnetic spectrum: red, orange, yellow, green, blue, indigo, and violet. The next highest level of radiation after the visible spectrum is ultraviolet, followed by X-rays, and the highest form of radiation would be gamma rays. Ultraviolet, X-rays, and gamma rays are types of radiation that we do not want to touch our skin. They can disrupt the molecules within our bodies and are harmful to us. Visible light and the radiation below is not harmful and will not penetrate our skin. Since visible light is the only portion of the electromagnetic spectrum that we can actually see with our eyes, we're going to study how matter can interact with light. The range of the visible spectrum we said is from 400 to 700 nanometers. And if we were to take white light from a light bulb or from sunlight, and we were to shine it through a prism, we could break that white light up into all of the colors that make up the visible portion of the electromagnetic spectrum. We could essentially separate white light into its component colors. Since electromagnetic radiation propagates as a wave, we need to understand some of the basic properties of waves. A wave is an oscillation or movement that can transport energy from one point in space to another. Electromagnetic radiation has two components. There's an electric component and a magnetic component, and both of them are perpendicular to one another. Notice that the electric field and the magnetic field are both represented by sinusoidal curves. They have a vector, meaning a direction, and a magnitude. When an electromagnetic wave passes an object, the oscillating electric and magnetic fields may interact with it. This interaction can allow us to identify what a compound is. As electromagnetic radiation moves away from its source, the positions of maximum and minimum amplitude, which are often called peaks and troughs, are regularly spaced. The peak-to-peak distance or trough-to-trough distance is called the radiation's wavelength. The symbol for wavelength is the Greek symbol lambda. This tells us the distance between two consecutive peaks or troughs. So we could choose, for example, this peak and this peak, which would represent one wavelength, or this trough and this trough. This would also represent the distance of one wavelength. Wavelengths are a length, so they have units of meters. But depending upon which portion of the electromagnetic spectrum we're in, the range could be from kilometers all the way down to picometers. There's a large range of wavelengths within the full electromagnetic spectrum. Another property of waves is their frequency. Frequency is described with the Greek letter nu. The number of wave cycles, or oscillations, that pass a specified point per second is described as the frequency. One cycle is one complete wavelength. Frequency is measured in units of cycles per second. Therefore, the units are inverse seconds, which would be 1/seconds, and that is equivalent to a hertz with the abbreviation Hz. If we look at our wave on the right, one complete cycle would have passed here, and another complete cycle would have passed here. This represents 2 cycles that have passed in a time period of 1 second. Therefore, we could say that the frequency of this wave is 2/seconds or 2 hertz. Another property of waves is the wave's amplitude. The amplitude describes the magnitude of the wave's displacement. The higher the vibrating charge bounces in a wave, the greater the height or amplitude will be. Amplitude is measured as 1/2 the height between the peaks and the troughs. So we would have this distance as being 1/2 between a peak and the baseline. Therefore, that would represent our amplitude. This could also represent our amplitude measuring to a trough. The amplitude of a wave corresponds to the intensity of that wave. And when we say intensity, for light we mean how bright that light is, or if it was a sound wave, the intensity would refer to how loud that sound is. One last thing about waves is since they are a sinusoidal curve, they're going to have points where they cross the axis at 0. Those points are called nodes, where there is a point of 0 amplitude. This would be an example of a node, as well as here and here. We will come back to the concepts of nodes later in the chapter. There is an inversely proportional relationship between wavelength and frequency. That means that 1 over the wavelength is proportional to the frequency of the wave. This tells us that as frequency gets high, wavelength must get low. And as wavelength gets high, frequency must get low. If we compare the 3 waves on the left and the distance that each travel in 1 second, or in other words, their frequency, starting here, that means how many cycles are traveling per second. So 1 cycle, 2 cycle, and 3 complete cycles per 1 second. So we could say that the frequency of that first wave is 3 hertz. And our next wave below, if we count the number of cycles per second, we have 1, 2, 3, 4, 5, 6. 6 complete cycles or oscillation in 1 second would mean that the frequency of that wave is 6 hertz. And at the very bottom, there was 12 oscillations per second, so the frequency of the bottom wave is 12 hertz. Since the wavelength is measured by the peak-to-peak distance, we can see that when the frequency was 3 hertz, our wavelength was rather long when we went from peak to peak. When our frequency was 6 hertz, our wavelength got a little bit smaller from peak to peak. And then when our frequency was 12 hertz, our wavelength was incredibly small. That shows the inverse relationship between frequency and wavelength. The speed of electromagnetic radiation in a vacuum is a constant and is commonly referred to as the speed of light. The speed of light is given the symbol lowercase c. It is a very carefully measured constant, but it is often rounded to 3.0 times 10 to the 8th meters per second. The product of a wave's wavelength and its frequency will give us the speed of the wave. Therefore, we can use the equation c equals lambda times nu, or in other words, the speed of light is equal to the wavelength times the frequency for a wave. The bright red color in fireworks is due to emission of light when strontium nitrate is heated. If the wavelength is 650 nanometers, what is the frequency of this light? Using our new equation, C equals lambda nu, we can solve for the frequency through the relation of the speed of light. Isolating our variable, frequency, will be equal to C divided by lambda. C will be 3.0 times 10 to the 8th meters per second. And since the speed of light is our constant, that's going to determine what we have to plug in for our units of our wavelength. Notice in the problem we were given units in nanometers. If we want them to cancel with the speed of light, we're going to have to convert them into meters. Our wavelength is 650 nanometers. And if you recall our conversion between nanometers and meters, the meter is going to be our larger unit. And so we'll call that 1. And there's 1 times 10 to the 9th nanometers in 1 meter. Our units of nanometers will cancel. And then our units of meters are going to cancel with the speed of light. And we'll be left with units of 1 over seconds, which is a frequency. So for this problem, the frequency would be 4.6 times 10 to the positive 14th inverse seconds. Or we can say units of hertz as well. WIOG broadcasts at a frequency of 102.5 megahertz. What is the wavelength of their signal? We want to use C equals lambda nu, and in this case we're solving for an unknown wavelength. So lambda will be equal to the speed of light divided by the frequency. We were given our frequency in units of megahertz. We're going to want to convert that into hertz in order to plug it into our equation. 102.5 megahertz. Our megahertz is going to have to go in the denominator, hertz in the numerator, and megahertz is the larger unit, so we'll call that one 1. And there is a million, or 1 times 10 to the 6th power, hertz in 1 megahertz. Our units of megahertz will cancel, and therefore we're going to have 1.025 times 10 to the positive 8th hertz, which is just equal to inverse seconds. Now we can plug that into our formula. C we know is the speed of light, which is 3.0 times 10 to the 8th meters per second, divided by our frequency in hertz that we just solved for, 1.025 times 10 to the 8th 1 over seconds, or inverse seconds. In this example, our units of seconds will cancel, and we'll be left with units of meters for our wavelength. And we should get 2.93 meters for our wavelength of that radio station. If you compare the wavelength units to our last problem, last time we had units of nanometers. That's because that would have been in the visible portion of the electromagnetic spectrum. Units for radio signals are much longer, so meters is appropriate. Not all waves are always moving. Waves such as radio and cellular waves that propagate through space are referred to as traveling waves. But there are also standing waves, which are also called stationary waves. These remain constrained within some region of space, and they are important in understanding the electronic structure of atoms and molecules. The simplest example of a standing wave is a one-dimensional wave associated with a vibrating string that is held at its two endpoints. Each of the endpoints are fixed, which restricts the number and type of possible waveforms that can be seen. The first wave only ends up having 1/2 of a wavelength that's possible between it. This is called the fundamental wave. The next three are referred to as the harmonics. Only those waves having an integer number of half wavelengths, or n, between the endpoints can form. So for example, the first fundamental wave could only have 1/2 of a wavelength form. In the first harmonic, we see 1/2 wavelength and a second half wavelength. In the second harmonic, we can see there's 1/2 wavelength here, another half wavelength here, and a third half wavelength. In the last harmonic, we have 1/2 wavelength, 2 half wavelengths, 3 half wavelengths, and a total of 4 half wavelengths. Therefore, in each case, n would be equal to 2, n would be equal to 3, and n would be equal to 4 to represent the number of half wavelengths that can occur between the endpoints of the fixed standing waves. This example is something called quantization. This means that only discrete values from a more general set of continuous values of some property are observed. Rather than there being any number of half wavelengths allowed, it's always fixed at being an integer number of some half wavelengths. Therefore, we say that the value is quantized. Also notice all of the three harmonics also have nodes, points that are not in motion. This would be an example of a node, as well as here and here. So when n equals 2, there was only one node. When n equals 3, there was 2 nodes. And when n equals 4, there's 1, 2, 3 nodes, or 3 points where the wave is not in motion. Another way to think about quantization is the difference between a ramp and a staircase. If we were to have continuous values, that would be an example of a ramp. Along the ramp, we could be at any point at any moment where I decide to stop. I could keep going and stop wherever I want. It's a continuous series of values. Quantized values are going to be determined based upon where I can stop on the staircase. I could be on this step, or I could be on this step, but I can never be at half a step. I could be at any step along the way, but I can only stop at those discrete specific values. That's what quantization is. In the previous slide, we saw the difference between continuous and quantization. A continuous spectrum of electromagnetic radiation is given off in a series of unbroken wavelengths. If we look at the spectrum for sunlight or solar radiation, we can see that there is a range of frequencies that spans from the UV region, and then it peaks in the visible region, and it starts to decline again in the infrared region. But we see all different types of UV, visible, and infrared radiation inside of sunlight. We can also see that the spectrum for sunlight very closely matches the spectrum of a blackbody radiator. A blackbody is the name for a convenient ideal emitter that approximates the behavior of many materials when it's heated. All a blackbody is an example of an ideal emitter. A good approximation of a blackbody that can be used to observe radiation is a metal oven that can be heated up to very high temperatures. At the end, the oven has a small hole, allowing for the light inside to be emitted. The emitted light can then be observed with a spectrometer, and the wavelengths and intensities can be measured. This would be the spectrometer at the end that's measuring the light that's being emitted from the blackbody emitter. The peak in intensity of light that's emitted from a blackbody oven actually shifts depending upon the temperature of the oven. At lower temperatures, such as 2500 Kelvin, the peak intensity is in the infrared region. As we increase to 3400 Kelvin, we can see that the peak intensity is shifting closer to the visible region. Once we reach 4400 Kelvin, now that peak intensity is in the red of the visible portion of the electromagnetic spectrum. And once we get up to 5500 Kelvin, the peak intensity is very high and it's in the yellow-green portion of the visible spectrum. Therefore, the peak intensity changes depending upon the temperature. This also explains why when metals are heated to really high temperatures, they start to glow a dark red at a high temperature. That would be maybe around our 440 Kelvin, where the peak intensity was in the red portion of the visible spectrum. And then if they get hot enough, they eventually become what we would say is white hot metals. And then you're seeing the intensities of all the visible wavelengths. Therefore, maybe you are over here, eventually heading towards the ultraviolet portion of the region. If you're viewing all the wavelengths of the visible spectrum at once, it would appear as white. Scientists were trying to come up with a mathematical expression that could model what was seen for blackbody radiation, but they were running into many issues. Through a series of groundbreaking experiments, it was shown that classical physics does not correctly describe energy transfer by electromagnetic radiation. Max Planck was a German physicist who was the first one that actually developed an expression that fit the experimental observations for blackbody radiation exactly. If we imagine that atoms that are making up the oven vibrate at increasing frequencies as the temperature is increased, these vibrations are the source of the emitted electromagnetic radiation. Classical physics would have us believe that the vibrating atoms could have any energy, meaning the energy could be continuous. But what Max Planck proved is that the vibrating energies have to be discrete values. In other words, the energy has to be quantized. The equation that he developed is E equals NH nu, where n is some whole number, 1, 2, 3, etc. And h is a constant called Planck's constant. It has the value of 6.626 times 10 to the negative 34th joules times seconds. Max Planck proposed that electromagnetic radiation instead can be viewed as a stream of tiny packets of energy. These tiny packets of energy were referred to as photons. His equation, often abbreviated E equals h nu, says that the energy has to be released in whole units of photons, where the energy being calculated is that of one photon. A second important experiment that was undertaken by Albert Einstein showed that electrons could be ejected from the clean surface of a metal when light having a frequency that was greater than some threshold frequency was shown upon it. Classical physics had believed that the energy of electromagnetic radiation was directly proportional to its intensity or its brightness, which would correspond to the amplitude of the wave. Einstein showed through this experiment that the energy of a photon of electromagnetic radiation is actually proportional to the radiation's frequency instead. E equal h nu, we can see that energy and frequency are directly proportional to one another. If we have a surface of a metal and we were to shine 3 different frequencies of light at it, 700 nanometers, no electrons are ejected. The frequency is too low to meet that threshold frequency to eject an electron. If we stream 500 nanometer light at the metal, now that wavelength has a high enough frequency to eject an electron at a certain velocity, 2.96 times 10 to the 5th meters per second. If we shine 400 nanometer light at our metal, now it has an even higher frequency, therefore the ejected electron has a greater velocity, 6.22 times 10 to the 5th meters per second. Therefore, increasing the frequency of light that you shine at the metal will increase the velocity of the electron that's ejected. Brighter or more intense light delivers a greater number of photons, whereas higher frequency light delivers more energetic photons. It was the more energetic photons that were able to actually dislodge an electron from the surface of the metal. Photons are a stream of particles, and this confirmed a concept known as wave-particle duality. Wave-particle duality says that radiation can essentially behave like either a particle or like a wave depending upon the experiment. The contributions of Planck and Einstein led to what we know now as the particle theory of light. The energy of a photon, or in other words, a tiny packet of energy, of electromagnetic radiation is directly proportional to its frequency. This comes from our formula E equals h nu. If we also use our formula C equals lambda nu and we solve for the frequency, we can substitute that frequency in to our energy equation. We could rewrite our energy equation as E equals hc over lambda. This allows us to interconvert between energy, wavelength, and frequency. What is the frequency in inverse seconds of radiation which has an energy of 3.371 times 10 to the negative 19th joules? We know that the energy of a photon is equal to Planck's constant, which is h, times the frequency, which is the symbol nu. If we rearrange and solve for the frequency, we will have the energy divided by Planck's constant. Our energy we were given in our problem of our photon, which is in units of joules, 3.371 times 10 to the negative 19th. And if we divide by h, which recall that h is equal to 6.626 times 10 to the negative 34th joules times seconds, we can see how our units of energy are going to cancel, and we're going to be left with units of inverse seconds, which is what we want for a frequency. So dividing by Planck's constant, 6.626 times 10 to the negative 34th joules times seconds. Joules will cancel, and we have seconds that were left with in the denominator, which is the same as 1 over seconds. Our frequency of this energy is equal to 5.09 times 10 to the 14th inverse seconds. A microwave oven uses radiation with a frequency of 2,450 megahertz to warm up food. What is the energy of photons in joules? We're going to once again use our formula E equals h nu, and in this case we were given our frequency. We know our frequency in megahertz. Since Planck's constant is in units of joules times seconds, we're going to have to convert our megahertz into inverse seconds in order for it to cancel. So starting with what we were given, 2,450 megahertz. 1 megahertz is equivalent to a billion, or 1 times 10 to the 6th hertz. And then we can convert our hertz into inverse seconds because those are 1 to 1. 1 hertz is equal to 1 inverse second. When we check our units to make sure they cancel, our megahertz will cancel, our hertz will cancel, our units of seconds will cancel because one's on the top and one's on the bottom, and we'll be left in units of energy or joules. Our energy will be equal to 1.62 times 10 to the negative 24th joules. Earlier we looked at a problem where we saw that the bright red color in fireworks is due to the emission of 650 nanometer light when strontium nitrate was heated. We converted that wavelength into a frequency earlier. What if we want to determine what the energy of that wavelength is? So what is the energy of one photon with this wavelength? And then also, what is the energy of a mole of photons? So we're going to have to use two different formulas here. We have E equals H times nu, and we also have C equals lambda times nu. If we solve for our frequency and substitute it into our energy equation, that will give us E equals Hc divided by lambda. This is going to be the formula we want to use because we have a wavelength and we're trying to figure out the energy. The numerator is two constants multiplied together, Planck's constant times the speed of light, and then we will divide by our wavelength in the appropriate units. So the energy is equal to Hc over lambda, which will be equal to 6.626 times 10 to the negative 34th joules times seconds, times the speed of light, which is 3.0 times 10 to the 8th meters per second, divided by our wavelength, 650 nanometers, but we're going to have to convert our nanometers into units of meters. So we have 1 meter on the top is 1 times 10 to the 9th, or a billion, nanometers in the denominator. Check that everything cancels. Nanometers cancel. Meters is on the bottom and the top, so that cancels. Seconds cancels with inverse seconds, and we're left in units of joules. So when we calculate our energy in part A, the joules that we get will be the joules of one photon. 3.06 times 10 to the negative 19th joules is how that's often reported. But we can also write joules per photon to be more precise. Even if we don't write joules per photon, it's just assumed that that energy is in units per photon. In part B, we want to know what is the energy of 1 mole of photons. So starting with our energy that we just calculated, so first we did A, now we're doing B, 3.06 times 10 to the negative 19th joules per photon. If we use Avogadro's number, we can figure out how many things per mole. We've seen things be atoms, molecules, ions, but things can also be photons as well. Recall Avogadro's number is 6.022 times 10 to the 23rd things per mole. Well, right now we want our things to be photons. Therefore, our units of photons will cancel and will be left in units of joules per mole. This gives us 1.84 times 10 to the 5th joules per mole.